inner product space. In Chapter 6, we defined dot product. U and V is equal to U transpose V. And we use dot product to define distance, norm, orthogonal set. And as a result, we have an orthogonal basis for Rn. We also have orthogonal projection on some subspace. And find least square solution. Here we would like to have something similar for vector space. And the answer is inner product. Something very similar to dot product for Rn. An inner product, abbreviated IP, on a vector space is a real value function. So it's a function that assigns to every ordered pair of vectors UV a scalar. And we use the notation UV is inside and bracket on the outside, such that the following axioms hold. First of all, the inner product of U and U must be greater than 0 if U is a non-zero vector. The inner product of U and V is the same as the inner product of V and U. The inner product of the sum and the W is the sum of inner products, UW and VW. And if we scale U by a scalar A and compute the inner product with V, then this is the inner product of U and V scaled by A. So inner product is a function of two vectors. And the function satisfies all these four properties. Whenever it satisfies all these four properties, then we say it's an inner product. A question: suppose we are given a inner product, and we define another function, also a function of two vectors, U and V. It's 3 times this inner product that's given to us. Is this function f also an inner product? That means, does it also satisfy the 4 properties? To see whether or not it's an inner product, we need to check whether it satisfies these 4 properties, right? So first of all, we look at f, u, and u. Would it be always greater than 0? If U and U is 3 times this F, 3 times U and U inner product, and because it satisfies this property, so we know for sure this is greater than 0. So the first property is satisfied. And secondly, we need to check whether FU and V is the same as FV and U. And because this inner product function satisfies this property, and we can readily verify that that's indeed the case. And we also need to verify whether it satisfies the third property, f of u plus v and w, is it the same as fuw plus fvw? The left-hand side is 3 times U plus VW, inner product. And the right-hand side, this is 3 times U and W. And then this one is 3, V and W. And then because this is an inner product, so it satisfies the third property. And the left-hand side is indeed equal to the right-hand side. The last one, we need to verify FAUV is the same as A times FU and V. And we can verify that this is true. So this is an inner product, yes. So what have we obtained here? From one inner product function, we have defined another inner product function. And we can make this number to be an arbitrary positive number, then we still get an inner product. So from one inner product function, we can get infinitely many inner product functions. An inner product function for a vector space is not unique. A vector space endowed with a particular inner product. That means we are using a particular inner product for this vector space. Then the vector space is called an inner product space. An example. Suppose C, a parenthesis and a closed interval AB, it's the vector space of a continuous real valued function defined on the closed interval A to B. So this is the collection of all continuous real valued function defined on this interval. And for all vectors f, g, and h, we define this function. The f and g is, this function of f and g is equal to the product integrated from a to b. The question here is the function that we have so defined an inner product on the vector space, C? So we need to examine whether or not the function we defined here satisfies the four properties that we talked about earlier. First of all, if we stick in f and f, would this be always greater than 0 for a non-zero f? So we throw in f, and this becomes f squared integrated over a and b. This is greater than 0 as long as f is not the zero function. So the first property is satisfied. Secondly, we need to verify if the function of f and g, the value of f and g is the same as g and f, the value of g and f. So we stick in f and g, and it's in the integration we can switch the order of g and f, right? So we get gf. So the second property is also satisfied. For the third one, we need to verify if this is true. So we have f plus g here, and h. This can be split into two terms, f and h in the g and h, and that's the value of the function of f and g, and the other one is g and f. So that's also true. Last one. CF and g is the same as f and g and scale by c. CF, we stick in CF. Since this is integration, we can pull c out, the constant c out. Then we get C, F, and G. And all four properties are satisfied, so the function that we have defined is a inner product for C. For the continuous function, the vector space of a continuous function over the closed interval a to b. An example of inner product for matrices. For a, b in M, n by n, we define the inner product AB is equal to trace AB transpose. We can verify that it satisfies all four properties of an inner product, and it has a name. It's an inner product on M, n by n, and it has a name called Frobenius inner product. Let's take a closer look at Frobenius norm and see what we are computing here. Suppose the C is AB transpose, then the trace of AB transpose would be the sum of the diagonal element of C, or trace of C. And this is trace of C. And C, defined as AB transpose, so the ith diagonal element would be AIK, and then the KI element of B transpose. The KI element of B transpose would be IK element of B. So when we sum up these diagonal elements, we get a double sum, AIK, BIK, and sum over all I and K. What does this mean? We are taking the IK element of A and the IK element of A at B. We take the product, and that's one term here. And for each element, entry of A, we find the corresponding entry of B, and we take the product. And that's another term here. So we are multiplying AB matrix element by element wise, and then take the sum. That's what this means. So if we are considering the inner product of A and A, we are basically summing up all the squares of entries of A. Within the product, now we can define the norm of a vector V. It's defined as the square root of the inner product of V and V. The distance between any two vectors U and V is the norm of their difference. When we use the Frobenius inner product, the norm is called the Frobenius norm. In Chapter 6, we have seen quite a few properties of the dot product, and many of those properties are valid for inner product. For example, the inner product of U and the sum is the sum of these two inner products. And Cauchy-Schwarz inequality is also valid. The inner product of U and V absolute value is less or equal to the product of their norm. For example, let's consider the example of a C, AB, and the inner product is defined this way. Then the inner product of a UV vector would be like so, F and G product integrated from A to B absolute value, and this is less or equal to the norm of F and the norm of G. So this is always valid for continuous function defined on the closed interval A to B.